Lecture 4, Work and Energy, starting off with Survey Chapter 7, Work and Kinetic Energy. This lecture is going to be a fair bit longer than Chapter 6's stuff, and we're also going to get into the first discussion of a problem that we're going to solve with a computer. So we're going to be solving a little bit of something with Maple today. Work for a constant force. The work done by a constant force is just force times d cos theta. Work is measured in joules. A joule is a Newton times a meter. Later on we'll see torque. Torque is measured in Newton meters, but it's an unfortunate situation where the same units technically describe a very different physical concept. Energy is not the same as torque, even though they have the same units. Scalar product. A scalar product, that is a dot product of two vectors, is given by the product of their magnitudes times the cosine of the angle between them. If the force is varying, then you really have to integrate. So locally, you can say that a little bit of work done is by force F is force F dotted with a little bit of displacement, but you'd have to integrate that if the force varies along a path. So you'd add up all the little displacements. In vector notation, that looks like this. You could also project the force onto the path if the path is in a straight line. A projection of u onto v, recall from algebra, is written like this, and it's u dot v over the magnitude of v squared times v. It points in the direction of v. It has a magnitude that's independent of v and represents the amount of u that points in the direction of v. Why is the magnitude independent of v? It looks like there's a bunch of spots where v shows up on the right here. We're dividing by magnitude squared. How can this be independent of v's magnitude? Well, we've got two factors of v in the denominator and 2 in the numerator. It turns out they cancel. So if you were to take v over, big V over, or vector v rather, over the magnitude of v, then that's equal to these unit vectors. So you could rewrite this as u dot v unit vector times v unit vector. And this certainly doesn't depend on what the magnitude of the original vector v was. Since this is equal to our projection formula, therefore neither did our projection. The projection of u onto the perpendicular of v, sometimes we'll need this as well, and this would be projection of u onto v perp, written like that, pronounced projection of u onto v perp, and it's from a triangle, just u minus the projection of u onto v, since u must equal its projection onto v plus its projection onto the perpendicular to v. Kinetic energy of a particle of mass m is half mv squared if it's moving at speed v. Work kinetic energy theorem says that the total work done on a particle is its change in kinetic energy. This would be the work done by all forces. Power is the rate of work, so it's the derivative of work with respect to time, or the force dotted with the velocity, at least in an instantaneous sense. It's very important to distinguish here between the work done by something and the work done on something. The work done by u on a box is the force of u on the box dotted with the box's displacement. Since the force of u on the box is negative the force of the box on u, this is negative the work done by the box on u at the same time. Second chapter for today is Chapter 8, Potential Energy and Conservation of Energy, Gravity and Elastic Potential Energy. So gravity potential energy is mgy, where y is height, and elastic potential energy is half kx squared, where x is spring displacement. Conservative and non-conservative forces. A force is conservative if the work it does on a particle moving between 2 points is independent of the path the particle takes between the 2 points. The work it does on a particle is 0 also if the particle moves in a closed path that's required. Some examples: gravity is conservative, so is a spring force. Force that's not conservative is called non-conservative force, such as friction. Potential energy functions. A potential energy function can be associated only with conservative forces. If a conservative force acts on a particle that moves along the x-axis from initial to final, then the change in the potential energy of the system equals negative the work done by that force. Let's think about this for a little bit. If we increase the height of an object, so suppose we take an object and we increase the height, then the gravity potential energy increases. What work did gravity do? According to this, the increase must equal negative the work done by gravity. Well, gravity did negative work because its force was down the whole time. So as we pushed the particle up, we had to work against gravity. Gravity was doing negative work on the particle. It's a conservative force because all of the work that it did on the particle, we're going to get back later. So it did all this negative work, but in the process, it was storing energy in its potential energy function. If we let go of the object, then gravity gives us all the energy back that we stored in it. That's kind of neat. Let's look at some extra information for 2P04. So in second year, we're going to introduce, you guys know about partial derivatives, and I'm also going to introduce here the idea of a gradient vector. You're going to see this in math, but not until next term in vector calculus. We're not going to use it very much in this course, but it is going to be a concept that we'll deal with. There's nothing too difficult about gradient vector. All it is a partial derivative in each direction. So if u is not a vector, it's a scalar. It's potentially a function of position in 3 space. The gradient of u is a vector with 3 components. The first component is the partial of u with respect to x. Second component, partial derivative of u with respect to y. Third component, partial derivative of u with respect to z. This is the gradient vector of u. So you might call this grad u. Technically, the del symbol is called a nabla, if you want a little bit of math trivia there. Most of the time, people would just call this grad of u or del u. This is the gradient of u. It's a vector derivative. So the gradient of u, the scalar, gives you a vector. Now, negative grad of a potential energy function is the force associated with that potential energy function. Let's look at an example here. So the gravity potential energy function is g times z. Actually, correction to that, it's mgz, as you know from earlier. So mgz, where z is the height, and then if we take the partial derivative of mgz with respect to x, first component, we get 0. Partial with respect to y, we get 0. Partial with respect to z, and then multiply by -1, we get negative mg. And sure enough, the force of gravity is negative mg in the z direction. And look at that, our formula worked. So we took the gradient of our potential energy function, and it, after we applied a negative sign, gave us the force associated with that potential energy function. If an object changes height by delta h, the work done by gravity would be the integral of this force dotted with displacement. It doesn't matter what the other components of its displacement were, because those are going to be killed by the dot product. So here's a vector notation symbol version of dot product, and we get negative mg delta h. We can take the force out of the integral because it's constant with position. When an object rises, the work done, gravity does negative work on it, and the gravitational potential energy decreases, and the opposite when it falls. Total mechanical energy is just the sum of kinetic and potential energy. Total mechanical energy of a system is conserved as long as no non-conservative forces like friction act on the system. We'll look at an example later on today where it gets very complicated because of a non-conservative force that varies with position. First question today, pendulum energy. A simple pendulum with mass m is released with the string length L held horizontal. What's the maximum tension in the string? Well, the maximum tension in the string would be the tension at the bottom, and we can figure out how fast it's going at the bottom by using conservation of energy. So mgh max is all transported into its kinetic energy at the bottom, so v bottom is root 2gl. Force at the bottom then would be equal to mass times acceleration, and we know it's accelerating in this circular path, so t is mg plus m root of 2gl squared over L, or 3mg. Second question for today is electric potential energy. We're going to get a chance to do some of these vector derivatives here. In a uniform electric field, like between the plates of a parallel plate capacitor, an electron experiences a force equal to a constant force in the x direction. Determine the electron's potential energy function, U at x, y, z, in response to this force. What we're going to do is try and do this the rigorous official way that'll work in general, and this is using a technique called partial integration. So we write out our gradient expression here. The force should be equal to negative grad of u, and what we're going to do is try and solve this set of 3 equations for u. So let's start with the z equation. We know that del of u with respect to z is 0. We can get u out of this by integrating, except because it was a partial derivative, when we do this integral, we add a constant h, which could depend on x and y, because if there was an x or y term there and we took a partial derivative with respect to z, that would have been killed. Okay, so u doesn't depend on z because del u by del z was 0, but maybe it depends on x and y. Maybe it's a constant with respect to, or it's a constant with respect to z, but that depends on x and y. All right, now let's look at the second equation here. We've got negative del u by del y equals 0, so we'll take the partial derivative of the u that we found so far, del h by del y, and set it equal to 0. Then we can integrate that thing partially with respect to y, and that gives us a constant that could depend on the other variables. Now, unlike u, h only depends on, well, actually, we know now that u only depends on x and y potentially, but h depends on x and y, so when we integrate that with respect to y partially, we add a constant that just depends on x, not on z. We've already established that it doesn't depend on z. Okay, so we know that u equals just a function of x, possibly, so we could take the partial derivative of that with respect to x, set it equal to the right-hand side of the equation up here. Now the third equation, the last one we're going to need to do, and del u by del x is negative f, but del u by del x from here was g prime, so g prime equals negative f, which means g is negative f times x plus some constant, and the potential energy is negative fx plus c. The potential energy function we can find from knowing the force can only ever be determined to within a constant. That's not just a case for this electric potential energy function we were doing here. That's true in general. Potential energies are always relative to some reference point. Okay, on to the final problem for today, and definitely the most difficult problem we've solved so far in this course. This is a block in a turnpipe. This is one that we're going to need computers to help with, and kind of getting towards what we're going for in this course in terms of setting up problems that you can't solve without using a computer to help you for the second half of it, where we actually get the numbers. So we've got a block of mass m, and it's in a turnpipe, so like what kind of thing you'd see at a skateboard park. It's of radius r, and it's a full semicircle there, and it's released from rest at the top of the turnpipe, height r relative to the bottom. That's how you know it's a semicircle. If the coefficient of kinetic friction is 0.3 and the coefficient of static friction is 0.7, find out whether the block will freeze under static friction the first time after release when its velocity is 0. So presumably it's going to get released, and then maybe kinetic friction is going to slow it down before it gets to the middle, or maybe it's going to rise up the other side to some height and then stop there. As its velocity is 0, then static friction will kick in. Either of those situations, we're going to try and find out the first time the velocity is 0 at the angle. So rather the angle where the velocity is first 0, and then find out if static friction at that point is enough to hold the block still. Now, if it stops on the way down from kinetic friction, as soon as static friction gets over it, as soon as static friction takes over, then it's just going to hold still. But if it stops on the way back up, where it rose to some height by converting kinetic energy into potential energy, then maybe it'll just it'll stop there. So if it stops on this side, then for sure static friction is going to hold it still. But on this side, maybe it will, maybe it won't. We're going to have to check. Okay. First part we want to do is set up the problem, but not actually go about solving anything. So we're going to try and get this to be into a differential or maybe integral equation form, all the equations that we would need to solve, and then we're going to actually solve it using Maple's help. All right. So we need a lot of things. We're going to need to write out what mechanical energy is. Mechanical energy is lost to friction. Work done by friction is the frictional force, mu k n, multiplied by the distance traveled. So it's negative mu k n because friction points in the opposite of the distance direction. So as we move more and more distance s, using s because it's kind of an arc length distance thing going on here, then we lose more and more energy to friction through mu k n. N itself depends on the angle that we're at. We're going to have to write out an expression for that before we can actually use this equation. The radial acceleration at any velocity is v squared over r, and this must be the sum of the force in the radial direction, force towards the center of the circle it's moving in, divided by its mass. The sum of the force towards the center is n minus mg cos theta, mg being down here, project onto the perpendicular to the ramp direction with a cosine. So we can solve this for the normal force in terms of the velocity. Starting energy is the gravitational potential energy. The energy remaining at any point is the starting energy minus the energy that's been lost to friction. So it would be mgr, the starting energy, plus the total work done on the particle, or on the block rather, which is mgr minus the integral of the friction work with respect to distance traveled. So, or I guess you would say plus the integral of the friction work, but the friction work is negative, so that's where the minus sign comes from. At any point, the velocity is determined from the remaining mechanical energy and the height y. Mechanical energy is u plus k, so potential plus the kinetic. And we can solve this for the velocity as well, if we like. What we're going to have to do is equate this energy to this energy, and see if we can get anywhere with that. The height is related to the angle, so we've got a lot of extra variables here, like we've got our energy in terms of the height and the velocity, and we've got our other expression for the energy in terms of the normal force, but we've also got relations that let us combine these. So normal force in terms of velocity, and we're going to need to find the height in terms of position. So the height is r times 1 minus cos theta. This is a little bit tricky to see. Consider the height of this block by dropping a horizontal line from the block over to the side. The height is y. This distance is r, right? The whole distance is r, and the distance from the top to the y coordinate is r cos theta. So y must be r minus r cos theta. Sure enough, that's what we got here. Y is r times 1 minus cos theta, or r times r minus r cos theta, and the distance traveled is s. S would be the integral of the little bit of displacement. ds would be the magnitude of r d theta. So the setup of the angles here, we've kind of said that the start is at pi by 2, and then the bottom would be at 0. So theta is decreasing under this coordinate system, and then continues to decrease over on this side. So theta is getting lower as we move along with this the motion in this problem. Okay, so ds integral of r d theta. So s would be the integral of r magnitude of d theta from its start to its end point. And since d theta along this path is negative, the magnitude of d theta is negative d theta. That's what the absolute value would do. It would multiply it by a negative 1 because d theta itself is negative. Taking this integral, it's just the change. So the negative sign reversing the usual direction, and we have theta naught minus theta as our magnitude of the angle change. Let's give a shot to checking this. When theta is equal to its initial point, we get 0. That works. At the bottom, when theta equals 0, we get s is equal to r times the initial angle, pi by 2. Yep, that's a quarter of a circle, so that worked. Okay, so our expression is good. S is r times theta naught minus theta. Then we can figure out what ds is for substitution into this integral here. ds is negative r d theta. So now going back to that, our energy expression in terms of initial energy and the work done is the integral of mu k n r d theta from theta naught to theta, where we've switched it back to plus because ds is negative r d theta. So that's where the pluses come from here. Substituting in our energy in terms of potential and kinetic, now we've got an expression which just involves two variables. We've got a theta and we've got a velocity. So what we're going to look for, this is valid at least until the block stops. We've considered the d theta being negative, which is going to be true along this whole path until the block first stops, and that's all we're concerned about anyway. After that, the block, maybe if it doesn't stop from static friction, would go back the other way, but that's not included in the range of the equations that we've got there. So we'd have to redo some of that for the next phase of the motion if it turns out that it doesn't stop at first. What makes this equation so difficult to solve is that the v here, which is inside this integral with respect to theta, has some unknown dependence on theta. Theta is our independent variable here. We're really looking for v as a function of theta, but it's trapped up in this integral. So we're going to need to get it out of there by taking a derivative. That's going to turn this into a differential equation. Because v only appears as v squared, before we do that, we'll have an easier time if we first define w, some new variable, let's call it w, as v squared. The triple equal bars means is defined as, so if you ever see w triple equals v squared or something triple equals something else, you don't have to say, oh, where did they get that from? Let me go back and have a check for that. No, it means it's being defined right now. So this is equal to that because we are currently making up a new symbol w and we're defining it as v squared. All right, so substituting that in, we get this differential, this integral equation, and differentiating it, we have gr sine theta plus a half w prime equals mu k times gr cos theta plus w. This is a first order linear differential equation. You'd see that if you were to put it into standard form. You dealt with this a little bit in first year and a fair bit more right now in second year if you're doing the math class there. So feel free to solve this on your own, but don't try to do the integral. Well, you could do the integral if you really want practice. In this course, we're going to be using Maple to help us with integrals a lot of the time. The initial condition that we need to solve this differential equation is w at theta equals pi by 2 is 0. So when theta is theta naught pi by 2, then we get we have the speed is 0. Right. Once you solve it for the first theta in this range, then what you would do is check whether static friction at this angle is enough to hold the block still by comparing Fs max to the component of gravity directed down the ramp, which would at that point be mg sine of negative theta. That's going to give you the gravity component down the ramp. Theta is going to be, well, assuming it passes the equilibrium point and goes up the other side. Okay, now let's look at solving this using Maple to help. If you've already done a bunch of Maple, you can give that a shot, or you can work through it if you're in Math 2Z03 or have already done a differential equations course where you know how to solve first order linear differential equations. Here's a reminder of that. Put it into standard form. So we put all the w's on the left and we clear the coefficient of w prime. And we leave everything that doesn't have a w in it on the right. Then we find the integrating factor, e to the integral of the coefficient of the 0th derivative of w, which in this case is e to the negative 2 mu k theta. Multiply both sides of the differential equation in standard form by the integrating factor, and then we can factor the left-hand side into the derivative with respect to theta of I times w, our dependent variable here. Now we can integrate both sides, saying that the integral of the derivative with respect to theta just cancels, and on the right-hand side we got the integral of this with respect to theta. We'll speed that up using Maple. So the way to do this in Maple is with this piece of code here that you'll look at in more detail in the tutorial. Maple doesn't add an arbitrary constant, so we need to do that manually. So we'll say that this is equal to the integral we got plus c. And now we want to apply the initial condition, which means substituting in that when we get that when theta is pi by 2, we've got a 0, and this is what lets us solve for c. We'll do that with Maple too. So we'll solve this substituted equation. Theta is pi by 2, and we've subbed a 0 in for w for c. And then we'll define w as that integral plus c divided by this term on the left, because that was still there, so we need to divide by that to get w. And there is our w written out. It's great. So what we're going to do now is see, are there roots for this where we expect, and where does the root occur? We're plotting from theta is negative pi by 2 to pi by 2. Really, theta is starting at pi by 2 and decreasing. So here's our start point, w0, that makes sense. It reaches some maximum, not quite at the bottom because of the friction slowing it down the whole time. And then as it passes through the bottom, it reaches a velocity of 0 right there. Looks like it's around negative 0.5 radians. All right, so it does instantaneously stop partway back up the ramp, somewhere around here at 0.5 radians. So what we're going to do is check. Well, first we'll find out exactly that number. We can use fsolve to do that. So we're gonna, this is a floating point solving. So we'll substitute in our kinetic friction component of 0.3, like we did to get the plot, and then we'll solve for w over gr equals 0. We have to tell it, we have to get rid of the gr, or Maple's gonna be a little bit confused about what that is. Maybe if we say that it's equal to 0, then it's not going to worry about it, but it's best to clear off those constants that we haven't told Maple what they are. So theta 1 is this. Okay, makes sense, about a little bit bigger than, or a little bit farther to the left than negative 0.5. Now we'll check whether the static friction at this angle is enough to hold the block still by comparing to our the max static friction to gravity at that point. Okay, so there's our max static friction term and our gravity using a coefficient of static friction that we had of 0.7, and it is. So this is larger than that, meaning that static friction will not be its max value, it'll just be equal to what it needs to be to counteract gravity, and the block slides down the ramp, comes up to the left-hand side, and stops as soon as it, and like stops as soon as it reaches its 0 point, and then just sticks there, freezes due to static friction. Very complicated problem that required a lot of computer stuff to solve, but very satisfying to be able to do a super difficult physics problem like this.